let's now talk about countability.
Okay.
So let's talk about the definition of countability first. What is countability?
Okay, so we're going to talk about the definition, but we're going to need to define something else after that in order to understand. So the definition of countability is that there exists a bijection, which we'll learn about shortly, between the natural numbers and whatever set we're talking about. So in this case, we're going to talk about the countability of the rational numbers.
Okay.
So there's a bijection. So a function between the natural numbers and the rational numbers with some special properties.
Okay, you know what? I think that's an important enough definition that we should write this out. Okay. So a set, say Q, or let's pick some other. A set G.
Yep.
Is countable if there exists a bijection between, did you say the natural numbers?
The natural numbers, yeah.
The natural numbers and the elements of Q. Am I correct?
Or G, as we've described it.
Yes, of G. Okay, so that is the definition of countable. Mm-hmm. Okay, so now we need to define what a bijection is.
Exactly, because that's what the definition essentially hinges on.
Okay.
And we'll write this out. So bijection's got two properties, and we'll go into what each one is. And as the name would suggest, there's two properties.
Yeah.
So the first is it's injective, and this is also referred to as one-to-one. The second is it's surjective, which is, and for anyone who's done French class, this might not surprise them, onto. Onto is kind of the other way of writing that.
So I think it's important to point out that the term bijection applies to functions or mappings.
Right.
Okay.
So it's a function from one set to the other, and if a function has certain properties, we can describe it as injective, surjective, bijective, whatever we want. Yeah. Okay.
So a bijection is a function that is both one-to-one and onto.
Yes.
Right? Okay, so let me write that out. So a function is a bijection if it is both injective also known as one-to-one.
Yep.
And surjective, also known as onto. Okay. So why don't we erase the definition of countable here, and why don't you tell us what one-to-one means?
Okay. So a function is one-to-one if, let's say you have an element in its domain and it maps to some element in its range. It's one-to-one if only one element from the domain maps to each unique element of the range. So in order to maybe formalize this in mathematical terms, why don't I write that out kind of as an equation?
Please do.
Let's say we have a function, and let's say we're going from A to B.
From some set A to some set B.
Yes.
Okay.
So A could be like natural numbers or real numbers or something like that.
Or it could be, say, the set of trucks that are on sale at a certain auto dealer. Okay. Or the set of colors in the rainbow. Okay.
Exactly.
Right.
We won't use colors in the rainbow here.
That's okay.
I don't know the math behind that. But,
that's okay.
Okay, so let's say we have f from A to B. Okay? And let's say we've got, let's say, x and and y, sorry, are elements of A.
Yeah.
So x and y, they're in A.
Yeah.
Okay, so let's take those and put them into the function. So let's say we have f of x,
yeah.
the function applied to x.
Yeah.
And let's say we know that f of x equals f of y.
Okay.
Okay. If a function is one-to-one, it's defined as when f of x equals f of y, you know for sure, or this implies that x equals y. Or, and some people like this definition a little bit more, or if, let's say, x does not equal y,
okay.
f of x does not equal f of y.
And could you just write 1-to-1 on the left here, just to signify that this is the definition of 1-to-1? Okay. So we're going to try to articulate this in plain English here. So suppose that this is the image of the function.
Yeah.
So this is the image right here of the image of y of f, the function f.
Yep.
Okay. So suppose that I have these are the elements in the image of f.
Yep.
So you're saying for every element in the image here, it must have come from. So this is the domain.
Yep.
Domain of f.
Yep.
So I think in plain English, what you're saying is, every element of the image of f must have come from one and only one element in the domain of f.
There's a uniqueness to it, right?
Yes,
so there's a unique element kind of in each set. So
right.
If you have the function, maps to some element, well, it's only going to go back to one element in the domain.
Right.
It's not going to it's not going to here as well.
Right.
It's not going to there as well.
Right. Okay. Now, I think it's important to point out here that it is entirely possible that some element in the image of f is not mapped by some element.
Oh yeah.
Right. If from it's entirely this could be our function. Actually, we want this to be 1-to-1. Okay. So we want this.
Right.
So here's here's the domain, and here's the image. Okay. So let's say I have another element here that maps to this.
Yeah.
Okay. But this element here is orphaned. There's no connection between this element and any element here.
Yeah.
This is still a 1-to-1 function.
Oh yeah, it's still 1-to-1.
Right.
Well, look at the definition, right? Like this has nothing really to do with making sure every element in the image has something in the domain related to it.
Right.
It's strictly when you have an element in the image and you have two elements in the domain. If the element in the image is the same, it's got to be the same element in the domain. That's what it's talking. We're not talking about what you were referring to.
Right. Okay. So that's 1-to-1. Now let's talk about onto.
Okay.
What does onto mean?
And maybe I'll leave that for 1 sec. So onto means that and you almost were just referring to this. Yeah. For every element in the image, there's something in the domain that'll map to it. So why don't we formalize that with a definition? So mind if I erase this right here?
Erase whatever you want.
Okay.
Erase whatever you want.
So let's say
an artist must have his or her canvas.
So this is onto.
Yeah.
That's say.
Can you just finish the left side of that O right there?
Let's get that. Oh, okay.
Yeah.
So this will be.
Thank you.
For all. Let's say let's use Z.
Okay.
For example, for all Z in B there exist some x in A such that f of x, that's a little, f of x equals z.
Okay.
So this is more talking about, we've got the image, the set B, got a lot of elements in it, and there, for this function to be onto, there must be some sort of element in A that you can put into the function and get B for every single element.
Right. So let's see if I can draw a diagram to illustrate this. Yeah. I hope that this is okay. So we have. Okay, so this is my domain.
Yep.
Domain of f. Okay, and here is my image. Image of f. Is that legible? Yeah.
Yeah.
Okay. Okay, so it means that for every element in the image must be mapped back to some element in the domain.
Yeah.
Now, it is entirely possible that some element that two elements in the image of f could be mapped to one common element in the domain. If the function is only onto, so let's ignore one-to-one here. Let's ignore one-to-one. If we're just talking about a function that is onto and only onto, it is entirely possible for one element of f to map to two different elements in the image.
Yeah, I don't see why not. Yeah,
right.
It definitely could be.